I like don't have any classes that actually.
I need those coins.
It's very of a math quiz.
No,
but
you
I'm math
don't.
quiz.
Yeah, I need more bag
I
storage.
need nothing this week. Yeah,
I have like
That's
950
my goal.
coins right
Like,
now.
I have like 140.
Because I just keep on saving them because I never see the box I really like. That's
Yeah.
what I'm saving up
This
for.
homework. But it-
Yeah, neither.
And so I gotta finish that, and then
Well, congratulations with the day of the first human in space.
Oh,
that's that.
so
No one of you selected research project on rocket fuels, but it was one of the possibilities. So, who we are and what are we doing? Everyone is so silent. I didn't get used to it.
Okay.
why does it look like his eye has a vein?
Oh, everyone agreed and decided what to research, right? That's it. Done. So let's. The main goal is to pursue your research areas, and in the meanwhile, I will entertain you by some additional pieces of information, but they're very, very secondary. Just if you just stand up and leave, or just open your notebook and start doing project, it will be better investment of time. So yeah, in the course of history, in the lectures we get through background information. In the lab, we got ideas how to write software and write hardware. And right now, you have already built models and you compute observables, or at least you plan. So light and matter. So here are some of your projects. I just, for my memories, try to put a graphical summary. And I was not lying. There was no intentional lie, but this procedure is maybe a little simplified in the way that it is not super general or just too general. Based on specifics of your choices, you may modify research procedure, typically in the making it more complex rather than more simple. And I don't care what is on the slides, but as I see from your choices, you do have about 2 general types of research projects. Well, more than 2, but roughly 2. So one is catalytic activity or adsorption-desorption experiments, numerical experiments, and another is interfaces of 2 materials. Right? So if you do reactions, and so there are 3 reaction projects. 1, 2, 3. Number 3 is checking emails or something.
No, he blame him.
And there is one person who also will do something relevant to reactions, but he doesn't realize it yet. So when you have molecule adsorb to the surface, and you can heat it up and see how it desorbs, so thermal desorption experiment. So it's also some sense of reaction, and then you either heat or set up momentum, and then you see how the geometry and electronic properties do change based on structural changes induced by heat or motion collisions. But there is another set of Daniel, you are in the border, you belong to both groups. Three, four. Interfaces. And in the interfaces, of course, we will do heating and see structural changes due to the heat, or we can induce bumping two interfaces into each other and see if any fun happens. But when you just explore ground state structure of your interfaces, you have already realized that you may need to split your model on A plus B, A separately, B separately, and then compare for binding energy and for matching of density of states. Whether the density of states of combined system can be represented as summation of the density of states of independent system, or they induce bending onto each other, whether they induce shift of energies. Another thing that was not in this list, but I will briefly mention today, and we will practice it next Wednesday on the lab, is inspection of charge transfer character of excited states. So if you create excitation in a true way or in oversimplified way, as we did with pairs of orbitals, the excitation may reside on species A, species B, or it may be charge transfer. In simplest case of metal organic electron goes to metal, hole stays on limits, or opposite. And if it is bigger interface, this is the main principle of photovoltaic when electron stays on one material, hole stays on another one. So you will need special tools to assess it. Of course, we can do drawing of hundreds of orbitals, but it is not the best opportunity. Some orbitals are good, but not hundreds. Directors, do not forget. Many directors, like 24 is not too much. What we did last time on the lecture, it is stickers that you did. Main procedure flowchart of DFT. You have seen it, right? So you do set equation for orbitals, and the orbitals determine the density, and here it should be potential density. That again determines the equation for orbitals. So if you are not scared by this expression, you are masters of density functions. And if you're curious how density is converted into energy or potential, there are some notations. And in the simplest way of the local density approximation, it is density in 4 third powers with some factors depending on spin polarization, if you have spin up and spin down. If you involve spatial derivative of density, then you are not local, but you are generalized gradient. So when we met last time, we were making slow start into the theory of excited states. There are many theories of excited states, and we start with the simplest, which is the extension of density functional theory. So density functional theory for excited states is called how?
Time-dependent?
Yes, time-dependent density functional theory. Please raise your hands if you did practice running jobs. 1, 2, 3, 4. Okay, majority. At least half. So, which question do you ask yourself when you run TDFT?
How many states do you want?
It is practical, technical. When you see it for first time, or when you hear it for the first time. Huh?
I don't know, like oscillator string?
Yes, so the main goal of time-dependent density function theory is to get spectra, oscillator strengths and transition energies. Do transition energies depend on time? When you run TDDFT, do your oscillator strengths depend on time? Do your geometries depend on time? So you have time-independent geometries, time-independent energies, and time-independent oscillator strengths. Why time dependence? What is time dependent? Why were there stupid people who call it time dependent, or is it a typo? I was puzzled by this question, and several people who just practically run it were not. When I first heard it, I was asking several people. No one was answering. Do not ask, just run. So, to run this job, you can do it in 5 minutes. You don't need lecture. But through a couple of meetings here in the lecture hall, we will answer the question, where is time dependence? Why it is inserted into the name? So one thing. And you already know the goal. Goal of steady state theories, practical, immediate goal for observables is to predict absorption spectra. Good. So I am still reviewing what we were doing last time. If we are immersed in the context of density function theory, then we agree that density determines potential, determines total energy, and the whole DFT procedure depends on density of electrons. Then we look how density of electrons is constructed. One uses this artificial orbitals of non-interacting electrons from auxiliary space, right? Main idea of quantum, but they generate sufficiently good density to reconstruct main observables. The equation for construction of density out of orbitals is just to take only those orbitals which are occupied, take their absolute value square, it's function of single position in space, and just add together. You did derive this equation in class, right? This one. Conjugated orbital itself, summation up to home. But if we want to be picky, rigorous, general, we can consider that indices of these two orbitals formally do not need to be the same. They can be different. And they actually do not need to run up to HOMO. They can go to the whole, every orbital that is available. And then instead of summation on the orbitals, we can put factor that can be 0, 1, or something else. And it will be a mask, a protocol, a record at which fraction, even pair of orbitals, contribute to total density. Okay? I didn't lie, I didn't deceive you, and I didn't contradict DFT theorems. So just for formality. And if we are speaking about ground state configuration of a molecule, then this matrix has ones on the main diagonal until HOMO, zeros on the main diagonal from LUMO and up, and nothing on the off diagonals. But you have already practiced, and the Fermi weight command in VASP. You know that you can artificially populate, you can promote electrons from HOMO to LUMO or further up. Right? You can make artificial population. What else? if the molecule is experiencing transitions, not just instantaneous transition before and after, if it is in process of being transported, transmitted from ground to excited and back, moving, cycle, circle, there is a chance that off-diagonal elements of this density matrix will be also non-zero. So, okay? And we can symbolically speak about the part of density matrix that from 1 to 4 corresponds to only originally occupied, to only originally unoccupied, and for cross terms, where one index covers occupied, another unoccupied. Okay, also just notation. So GG, GE, EG, EE. Ground, ground, excited, excited. Ground, excited, excited, ground. Also, I didn't introduce anything new, just notation. Now, any or vast majority of characterization techniques for characterizing materials is interaction with electromagnetic field of different frequency, different intensity. Any objections? No. And if it is optical spectra, it's just electromagnetic wave in the optical range. So there is a so-called perturbation theory that you may have been time-dependent perturbations, not just regular, that you may have been exposed or you will be exposed during your career if you stay in science. And it is unavoidable if you do some sort of theory. So if you consider that your electromagnetic field is weak, not like first week of May, but not very intense, then the section of the density that corresponds to occupied orbitals will stay almost unchanged. The segment that corresponds to transitions from ground to excited or back will be linearly proportional to intensity of electric field. And the one corresponding to creating actual excited populations will be proportional to the square. And you love Taylor series since you're here. So calculus didn't kill you and you came here. And you know that if there is a power series with with powers going higher and higher, and the argument is smaller than 1, then you can drop higher order terms, right? So you can drop second order term and keep only the first. So again, it is not yet Rigorous thing. I'm not doing derivations of final equations, but the goal of excited state theories, and more specifically time-dependent theory, is to find out this first order correction to the total density created by external radiation. First order correction to density. And if you find it, we can find the rest of observables, including spectrum. So we did stop at about this place last time. I don't know about you, I got tired when I saw this equation. So this is only example how to expand this block, building blocks of the density matrix in explicit form. So each of these rho GG, rho EE is a matrix, right? And it has two indices because it represents contribution of a pair of orbitals. So if we are looking only on the GG segment, it is here. Right? And if we predominantly stay in the ground state, we'll have rho minus 1, and it will start from rho 1. Right? All other elements will be 0. And all other elements of other blocks will be zeros as well. But I'm trying to avoid rigorous derivations so that first we get main idea, and then if you have steam and interest, we can go into more details. But the main purpose is not to kill interest and get main idea first, or maybe only main idea. So as you support, as you agree, since no one objected, it means that you are supporting. The idea that only rho GE and rho EG, the off-diagonal blocks of density matrix, are perturbed when system is interacted by weak electromagnetic radiation. So technically, mathematically, the goal is to find out. No, I will do. No, I will do. Zero. So we need to find this matrix and this matrix. I learned something new today. I learned how to highlight. So this one is assumed unchanged in the first order correction. This one you'll get changes only in second order correction. And this one will get non-zero contributions in the lowest order of taking into account interaction with electromagnetic wave. So the goal of excited state theory, particularly time-dependent density function theory, is to find these contributions, find this matrix. By the way, you may feel irritation because you came here to get entertainment, not strong intellectual challenges. Why should I read through so many numbers? And how are they related to real life and to my spectrum? So, if the excited state is the lowest, if you have only the lowest excited state, contributed by transition from HOMO to LUMO, only this element, rho or U, will be non-zero. The rest will be zeros. Okay? So it is which pair of originally occupied and originally unoccupied orbitals contribute to excited state. Okay? So we need this matrix. And in most cases, this one is that doesn't differ much. They are to some sort of conjugate. Do you like matrices?
Love them.
Huh?
Love them.
Only one person loves matrices. What do you love better, matrices or vectors?
Vectors.
Yes, I agree with you. Vectors is simple. It's just a list of numbers. So we need matrix, but we love vectors. Why don't we write the matrix in vector form? Huh? It is long, but there are benefits. Vectors are simpler to perceive by human brain. A lot of codes and tools and subroutines has been written to process vectors and how matrices affect the vector. If you are having fun of programming, scientific programming, and calling subroutines, you have, it's called Graphical. You have heard about this abbreviation. You may or you may not. So if you are programming in C++ or Fortran and you need to diagonalize a method, you do not write a code to do it. You just execute a subroutine from a package. And for most of the mathematically intense operations. Otherwise, our development of civilization will stop if we recode any simple operation. So we need to find this matrix. And matrices are often found by procedure of eigenvalue procedure. So we just need, if no one objects, which means you support of storing matrix, I like this much more, store matrix as that. And now we agree on this format of storing matrix as a vector, and we need an equation that will find this vector. Okay? And the meaning of this vector is relative contribution of a pair of elementary excitation into the excited state. Of course, this vector or pseudo vector will be different for each excitation energy. So we need to find energies at which system does respond to excitation, because resonance. If system is off resonance, nothing changes. And for each resonance frequency, you need to find such vector. The lowest excitation will be homo lumen. For others, it will be more and more. Okay? Make sense? Good. Alisa, do you like long notations of vectors?
No, I like
No,
them.
good. I do not like them as well. You wanted to say something else?
Oh no, I just like them. Like it's hard for me. I never learned it going up and down, so like my brain likes it.
Mine too.
Reading.
I do not. I hate this long notation. And why don't we abbreviate this strange long pseudo column by something very simple, like X and Y? You're with me? Okay, good. Approved. So we need an equation for X and Y. X and Y are unknown. Find X and Y. So main goal of time-dependent density function theory is to find X and Y. Good? Yes, find X, find Y. It was, I planned to stop here last time, but right now it will be physical, logical lecture, and physical lecture will not overlap. It will be a little phase shift. There, and I didn't have time to change slides, therefore I need to repeat refreshment of previous information once again. So, oh, it is not wrong. For ground state, Fermi distribution for yes, zero temperature. For logs, and we need to find X and Y. Okay, this is a plan of what I want to go through. If you get through, it will be great. If not, we'll continue after. If you know each point in this list, you can stand up and leave, or just open a newspaper and read fresh news. Before we continue with time-dependent density function theory, TDDT, which basically you already understand what it is and how it works. You just need a little more details. But before we go there, I wanted to do something that can be done without TDDT. It can be done without our oversimplified Fermi weight populations. I want to open an intrigue that Christian was intrigued for half a year, and Austin probably was not intrigued since he dropped the course. Or no, he was intrigued, but he burned out. He was not able to sustain this intrigue. The intrigue is reorganization of structure of molecule upon photoexcitation. The reason for Stokes, Frank-Condon factors, tolerance. In different areas of science, there are different abbreviations. So, if you were practicing spectroscopy in your experimental life, or if you were taking courses in spectroscopy, maybe organic spectroscopy, you have seen this figure. Who hasn't seen figure like this in previous life? Okay, who has seen this figure before? Everyone. My life is easy. So you have ground state, excited state, and this point, only one point, corresponds to geometry. So geometry is multidimensional, but we put it on one axis, right? So it will be, the geometry will be determined only by one coordinate if it is diatomic molecule. So it is literally correct figure for diatomics, and for all others it is symbolic representation. Upon photoexcitation, you have R0, geometry at ground state. As soon as you excite and let it relax, the potential energy surface for excited state can differ from potential energy surface in the ground state. The excited differ from ground means its equilibrium position is different. This one will be R excited. Excited state gives different geometry. And since potential energy surface is not flat, also will give different transition energy, right? And potential energy surfaces are often multidimensional and complicated things. But there is a way to approximate it, to project multidimensional potential energy surface onto one-dimensional figure, assuming that when you photoexcite, and it experiences rearrangement along specific path in this multidimensional space. And this specific path is referred to as reaction coordinate. Okay? So there is a way to project in one dimension. And what else? Lisa, do you like shape of this potential surface? Do you know which equation to fit it into?
I mean, just use.
No, if you want a function that will coincide with this shape, which function should it be? Can anyone answer it immediately?
Anharmonic oscillator?
Anharmonic oscillator, maybe Morse potential, well, something not immediately easy. But if the elongation, if the distance between ground and excited states are small, why don't we assume that both potential energy surfaces are harmonic oscillators? Okay. And in order to determine curvature and reproduce the harmonic oscillator, it is sufficient to know just 2 points. Same as for, if you in Euclidean geometry, if you know 2 points, you can put straight line across. With one can do the same for parabolas. One can reproduce their shapes. If you know that one of the points in this pair stays in the minimum, not any 2 points, not sufficient for parabola, you need 3. But if you know for sure that one is in the minimum, then 2 are sufficient. So what are the coordinates of these 4 magic points? So optimization at ground state, optimization at excited state, energy of vertical transition when we keep ground state geometry, and energy of vertical transition when we keep the excited state geometry, right? This, I do not see immediate necessity for any of your projects to do it practically. This would be most important if you would have donor-acceptor pair of 2 molecules that get elongated substantially. But it's better to mention now. So the project that Christian and Austin were doing in PChem were based on calculations of these 2 points based on the Fermi weight optimization for excited state. So with this little hint, you should be able to reproduce the results that you used as an input for your project in PChem. Okay? But when this was just a little note, so that I do not forget and tell it to you now, because you may decide that you need it for your project. In the didactic, academic part of the lectures, when we focus on TDFT, we will consider only vertical transition. We will assume that geometry is frozen. Otherwise, we will do too many things simultaneously. What else? This frequency is typically bigger. This is typically smaller. Blue and red. And the difference of this frequency, emission occurs, right? At this frequency, absorption occurs. Their difference is referred to as
Stokes shift.
yes. Yes. And if the frequency of these parabolas turn out to be steep enough, so not very flat, if quantum nature of these parabolas are important, then the transitions may occur not at any frequency, but only at discrete differences between quantized vibronic levels, right? So this situation is very frequent in the molecular spectroscopy. Yes?
So what happens if you do this and try to do an optimization of the excited state, but then so you have 2 excited states that cross, and the originally higher one actually is now the new lower one? Does that ever happen?
Yes. It happens all the time.
It's automatically taken care of?
No. It is not included into standard procedures. You cannot use black box. You need to think creatively when you meet such situation. So, what do you want me to write here under the axis? I'll write both lambda and energy, right? So they're complementary, respectively. So the absorption spectrum happens at higher energies and lower wavelengths, right? And the emission spectrum happens at lower energy or longer wavelengths. Right? So absorption. So absorption corresponds from going to different vibranium states here. Higher frequency emission going from lowest vibranium state to several vibranium states there. And they occur at different frequencies. It is a very typical picture for experimental spectra of organic chromophores. Okay. I'm yet steering away from TDDFT, but making little notation that primarily targeting but everyone else will benefit. So there was another intrigue how to project three-dimensional density onto one dimension. Okay. So if you have orbital or anything else, you can plot three-dimensional isosurfaces of orbitals or total density or potentials. And there is a practical necessity to analyze them. So what I'm going to show now, it is more related to the labs. But who knows how they will go, so I'm going to give you a heads up now and we'll try it next step. Try to prepare molecular dynamics which is needed for your project and launch it, make it running. You also, switching to different mode, you also may get strange emails authored by NERSC.
Oh,
National Energy Supercomputer Center. Just agree with everything.
I was wondering what that email was about.
Huh?
Is there anything we're supposed to do with
It
that?
tells you it created a username and stuff.
It created username and there could be a link for like setting up your password and signing the user agreement. Putting boxes. I'm not going to do that. Right? We will use this accounts next lab and just make sure that it is activated. Some of you have already had accounts there. When I was trying to go, it tells, no, this person is already in the system. So when you have three-dimensional distribution, there are three ways to analyze it. Just plot as is, and if you have many orbitals, you probably already got exhausted with homeworks, where you plot orbitals. If you're not got exhausted with it, it's my fault. I needed to to create this driving force and make some scary homework with 100 orbitals. But there is a bypass way to deal with it in least effort. So we draw orbitals not because they are pretty, not because of aesthetic pleasure, although many of us just like looking at them. We have purpose to analyze charge distribution, localization, formation of charge separation excited states, formation of dipole on a surface, such things. And there are additional ways. So first, one can project three-dimensional distribution in one dimension, just integrating over it. Right? Agree? So, So in the directory where you have partial charge densities, you type perf in band integrate, and then it will perform this operation. We'll go over when it will time for that. Another thing is to make integration over all three dimensions, but multiply your distribution by position value. This will be expectation value of position. And if you compare expectation value of position for one orbital, another one, those that are localized on species A will have value centered at this species. That will, the ones that will be localized at species B will be centered there. So you can, to analyze vector is much easier than the distribution. And if your species are offset along one dimension, or let's say Z, then X and Y components of the vector will be zeros, and you need to compare only Z projection. So you can perform this operation for like 100 orbitals and quickly sort them out. Tell which orbitals belong to species A, which orbitals belong to species B. Those of you who are working on interface of materials may benefit of this. Here are examples. Orbital localized in one area, orbital localized in another area, and if you integrate along 2 dimensions, it becomes one-dimensional projection of orbital. Okay? Okay. Done with side stuff. Now we are returning to time-dependent density functional theory, but again, we are not jumping too quick. I'm going to repeat a statement that I already heard in the goal of time-dependent density functional theory is to reproduce absorption spectra in the visible range, right? Yes? Let me jump. I will return to this slide. Yes.
I figured it out, by the way. That's the absorption.
Yeah, good. So, if our goal is to depict absorption spectrum of our material or our molecule, it means we need continuous function of absorption as function of energy excitation. You can put H bar omega. So in incident value. And then you need 2 sets of data. They resonant transition energies, right? And in simplest cases, those are just energy differences between occupied and unoccupied orbitals. Later on, it can be more complicated. And oscillator strengths corresponding to this resonance energy. So these 2 sets of data are expected output from TDDFT. So practically, if we don't care about any theories, we just need to do applied research. We need 2 sets of data. On one hand. On the other hand, I was already telling you that by some reason we need to do this favored letters of Alyssa. Instead of long vectors, we used letters X and Y, right? Is the goal of lecture to torture young brains? No. Even if it happens, it is not our original intention. So everything should be connected logically. It's a fault of instructor if it doesn't seem connected. But this X and Y vectors, pseudo vectors, that we are going to find, or TDDFT theory is going to predict, are intermediate data that allow to compute oscillator strength. Oscillator strength, well, our global observer is spectrum distribution, but our local data that we practically need to compute are oscillator strengths. So our task, if you would live at the times when TDDFT was not yet designed, and we need to hire a group of theorists and tell, design new theory for us. The goal is just to predict oscillator strength. Do whatever reverse engineering or however you can do it. So we were happily surviving without TDDFT. We were doing independent orbital approximation. Okay? So what we did, we multiplied function orbital with index I, function orbital with index j, with a little star here, and with r in between. And then we thought that it is transition dipole vector for a given transition, for a given pair of transition represented by pair of orbitals, right? At least one should have it, because it is your favorite subject. So as soon the vector has three components that you have shown where they are located in the oscillator strength file. Last three columns. If you want to find it separately, it will be only x instead of vector. Same equations for y and z. So I do not like 5. So 3 projections. And then we do absolute value square of the vector, which means row by column, dx squared, dy squared, dz squared, right? And when we multiply it by some additional constants, it will be oscillator strength. So we do have procedure to get oscillator strength, but it is based on the approximation of independent orbitals. Why we are not happy? Why we need new theory? Why independent orbitals are not sufficient? So I saw 4 hands answering the question, answering yes to practical practice in running TDDFT, right? Can you lift your hands once again? 1, 2, 3, 4. Okay, now it is 3.5. You anticipate provocation from me. So imagine what would you hear back from reviewers if you try to publish spectrum based on the independent orbital approximation.
Does the electric field cause fluctuation in the orbitals?
So in this approximation, one assumes that photoexcitation doesn't change shape of orbitals, doesn't shape energy offset between orbitals. It means that when you promote electron from occupied to unoccupied, the excited electron doesn't interact with created hole. It neglects electron-hole attraction. But in fact, even if it is localized, they attract, and often this attraction has a negative stabilizing contribution to the energy. So if you do same functional TDDFT results, it can be lower energy than same functional, same object in independent orbital approximation. So there are several interactions that are skipped in the independent orbital approximation. And to in the hunt for precision, one needs some more advanced theories. On one hand. On another hand, how do we know that excitation is composed? Do you need to go, Russell? Do you need to go a specific time? No? So how do we know that an excitation of resonance condition will be composed only on one pair of electron and hole? What if our valence band top occupied orbitals and conduction band bottom unoccupied orbitals are degenerate? Then it is very likely that lowest excitation will include superposition of multiple electron holes, but it will be one excitation. So this concept is missed in our independent orbital approximation. We need to be able to compose one transition out of multiple electron hole pairs. So it is another reason for creation or learning TDDFT. So it creates correction to absorption spectrum in transition energy, in superposition of multiple electron hole pairs contributing to excitation, and some others. I wouldn't be able to reproduce this with close eyes. We need to remember only that it is proportional to square of the transition density vector, and the factors are not quite constant. Well, pi is constant, mass of electron is constant, charge of electron is constant, Planck is constant, pi is constant, but transition frequency is not constant. So it will be different frequencies. There is a contribution to oscillator strength, but it is included in the code. So when you do oscillator strength, it is already there. What are Einstein coefficients? Have you seen or read about Einstein coefficients? Give me more service. No? No? Einstein coefficients? No? Yes? Yes? Einstein coefficients? Okay. Good. You don't need to keep your hands with Einstein coefficients forever. So when we do have interaction between light and matter, there are, right now I'm not deriving anything, I'm just giving phenomenological facts. If needed, we'll go to details, but let's just skim through facts. If we have, say, molecule and light, electromagnetic wave, which processes can light impose, which process can happen to a molecule? Do not answer. I'll give more details. The question is tricky. Before interacting with light, molecule can be excited or in ground state. The light can be high intensity light from source, or I need to draw something. I will ask you to answer the question, but I need to give some background information. Lasers, yes? You know how to build laser at home. Probably it will not work, but you know you need two mirrors and active media and source of light. Right? So optical resonator, two mirrors. And the electromagnetic wave of given frequency forms standing waves. And then it is the same frequency, same number of nodes, but amplitude can be different. Right? So the amplitude of this standing wave mathematically behaves in the same way as harmonic oscillator. Intensity of mode. So the standing wave is called mode. Intensity of mode in a laser resonator behaves as harmonic oscillator. which means it is quantized. Give me a sign if you are not happy if I'm going too quick. Okay, everyone approves and remembers and takes notes or memorizes. Oscillator. So, yeah, electromagnetic wave. Which means if we have the intensity high, it just goes force and back at given energy. But if we approach lower energy of this oscillator, it will be quantized. Which means that even if you do not have any sources of light, if you do not have flashlights, if you do not have stars, if you have just free universe, which simply obeys laws of nature, free space, no atoms, no electrons, no stars, no flashlights, only electromagnetic field performing 0-point oscillations. So there will be non-zero intensity of electromagnetic field even in vacuum. Okay? There is a little bit of light everywhere, even if there are no sources. So now the question. And the answer is Einstein coefficients. You may derive answer by your, if you shout it out loud quicker than myself, we will call it Einstein coefficient, but whoever will be first. So, for interaction of molecule and light, which processes are possible? Give the number of processes which are possible, and if possible, name them. Alisa wants to be first because she's smiling. No, some elementary process of interaction between light and matter. You know, you can to name at least one. Excitation. First, excitation. So it will be not Einstein coefficient, but it will be Robert's coefficient. So absorption. Robert's coefficient. Okay. So you may assume that if I'm asking this question, the number of processes will be a little bit more than one. Huh? Photoelectric effect, it is absorption to the continuum of unbound states. So it's also credit of Einstein, but it is to some sense very similar to absorption. So you go from ground to some excited state. Yes?
Is there one that's a transition between states or relaxation?
Okay. So what do you, your name will be there, but you need to be more specific. So you, Braden assumes that a system is in the excited state already. And due to interaction with light, it may go to ground state. Yes. But with which light doesn't interact? With light from source or with background radiation?
It's called stimulated emission.
Yeah.
Stimulated emission. Okay.
I forget why.
Okay. So
I think it has to be a light source for that.
Yeah.
Stimulated
Because
emission.
then you also have spontaneous emission, which doesn't need a light source.
That's true.
Okay.
Yeah, there's two.
So stimulated emission, it will be weight coefficient. And number 3,
Spontaneous emission.
spontaneous, it will be shock coefficient. So now we do have Robert's weight-shock theory of interaction of light and matter. RWS theory. So there is a absorption and two types of emission. Stimulated, which means the transition down in energy occurs due to interaction with strong light from the source. And there is another process when transition down happens due to interaction with background radiation. So no one stimulates it. It occurs spontaneously, therefore it is spontaneous. Typically it happens much slower, but it does happen. So induced absorption or induced emission occur typically on the order of like 100 femtoseconds, maybe 1 picosecond quick, depending on intensity. Spontaneous emission is, even in very optically active systems, occurs longer than 1 nanosecond, can be milliseconds. It is the reason why all chemicals that we purchase from Sigma Outlet are in ground state, because postal service delivered longer than 1 nanosecond, and everything goes to ground. Okay? Induced excitation, induced emission, and spontaneous emission. They all do depend on square of transition dipole on oscillator strength. But inverse of the spontaneous emission, it's a rate so and the rate of this spontaneous emission determines lifetime. How long the system will stay excited if it was excited. Okay? It is also one of the observables that you can compare to experiment. And based on this equation, if you do have oscillator strength and energy of transition, you can compute it. And you can compare it with experiment. If you take the oscillator strength from independent orbital approximations, the number will be a little bit off. You can compare only qualitative trends. So for this excitation, it will be longer lifetime, for another will be shorter lifetime. But if you do TDDFT, there is a chance that you will hit very close to experimental data or predict something that experiment was not. So one of the practical benefits of the course, you can predict radiative lifetimes of the excited states in molecules and nanostructures. And I do not need to instruct anything else. You already have the data for oscillator strengths. You know how to compute it. Right? One of the versions of the codes actually make one more column, and it just writes down lifetime. Favorite equation. Yeah, favorite equation. So what do you in 1 week ago? London told us that something like, I'm suffering from collective editing. Something like this. And during the collective editing, instead of delta, there was symbol D. So it took probably the longest time to recognize it. So formally, if one can set up each line with delta function in infinitely small bit. But practically, you know that Stokes shift, vibrations, oscillations, Doppler, there are several mechanisms for line broadening. Therefore, instead of infinitesimal sharp delta, it's not actual delta, it is delta sub sigma. So delta is finite with So we replace delta function with Gaussian with finite width. And it is how we construct absorption spectrum. If you compute them and report them in your written reports, which will be mandatory for the course, do not forget to mention. Just copy paste from notes or type it into question editor. But I'm teasing yourself and myself, but those are independent orbital approximation energies. We need energies and oscillator strengths not from here, but from TDFT, from X and Y symbols. It's fine. We already covered this. Let me see. Maybe I think I'm very excited to tell you about excited states, but it is 12:15, and maybe it will be a reasonable thing to start next meeting. Unless you all tell, give us more, give us more. So, anyone votes for departing in peace? 1, 2, 3. Anyone votes for sitting longer and entertaining more material? Refrain from voting. Okay. By majority of votes, we are finishing our discussion here and accumulate energy for our next meeting. Do not relax on weekend. Invest all of your free time in running molecular dynamics of your models. So stop here. Stop here, and it will be lecture number 26.
I do feel like we went through more lectures last semester.
Huh?
I don't know.
I plan to finish in 30, but there will be, in addition to deductive, there will
we had
be
3 a week.
3. There will be 1 presentation, and at least 1 for grading written reports, like improving as we do on group meetings.
Yep.
And maybe 1 more with instruction how to write papers. So, and finish. And Brendan wanted configuration introduction. Yes.
Okay, so I'm using the again. So the only file that I need is
You got one already.
Yep.
I have that I do, like more so the category.
You catch Pokemon on the way?
Who's checking to see if there's a raid battle in here?
You can transfer all 4 files.
Oh.
Postcard, card, keyframes,
Okay.
card, and in the card just change the number.
Also, I do not fully remember how to transfer files from directory to directory.
Okay.
So,
Very good. I do think that this information needs to be on the recording.
oh no.
So this is fine.